Okay, Chemistry 1411. This is practice exam 3, second half. If you go to my YouTube video, I cover the first 18 questions, and now we're going to take a look at questions 19 through to the end. Well, question number 19 says, which of the following is going to yield a buffer solution when two equal volumes of the two solutions are mixed? Well, you should remember that a buffer solution is a mixture of a weak acid and its conjugate base, or conversely, it could be a weak base and its conjugate acid. Well, if we look at A, you see the acid would be a mixture of carbonic acid and hydrochloric acid. So we're just mixing two acids here. That's not going to give us any base whatsoever, so that's not going to give us a buffer solution. The next one is that we're mixing carbonic acid with potassium hydroxide, but we have equal volumes with the same concentration. And so if you were to do that, if you were to combine carbonic acid, okay, with an equal volume of potassium hydroxide, you're going to end up with, you're going to end up neutralizing that acid, all of that acid. So that is not going to make a buffer solution. If we look at the next one, we have two acids, carbonic acid and hydrochloric acid. And if we look at E, we have potassium carbonate and potassium hydroxide, both of which are bases. But if we look at D, we have carbonic acid and potassium hydroxide. Okay, so if we're adding equal volumes of those, okay, we can assume that we would have, let's say, 1 liter of each of these. And if we combine carbonic acid plus potassium hydroxide, we end up making the bicarbonate ion plus water, like that. Okay, well, if I assume, and I'm going to assume that I have 1.0 liters of each, right, because I have equal volumes of the two solutions. So that means that I would have 0.10 moles of carbonic acid, and I would have 0.050 moles of the potassium hydroxide. So that means that the hydroxide is going to be my limiting reactant. I'm going to eliminate the potassium because it's a spectator ion. And so initially, if I have both of those, I'm going to have a change where I'm going to remove 0.050 moles of this, and I'm going to remove 0.050 moles of this, right? And I'm going to form 0.050 moles of the bicarbonate ion, so that at equilibrium, I have some of the bicarbonate, of the carbonic acid left over. I have none of the hydroxide, and I have some of the bicarbonate ion formed. And I have an equal amount, right? If I assume that it is 1.0 liters of each, then it means that at equilibrium, the concentration of my bicarbonate is going to be 0.050 molar, and the concentration of my carbonic acid is 0.050 molar, and the concentration of my bicarbonate ion is also 0.050 moles per liter. And so I have an equal concentration of the weak acid and its conjugate base, and so that is going to make a buffer solution. Number 20 says calculate the pH of a buffer solution that has 0.25 molar benzoic acid and 0.15 molar sodium benzoate. And so benzoic acid and the benzoate ion are conjugates, right? Benzoic acid, C6H5CO2H, we know it's an acid because it's got acid in the name, and we know it's a weak acid because it's not a strong acid, is it? Not one of our strong acids. Now the benzoate ion, C6H5COO-, this is our conjugate base, which is not a strong base. So this is going to be a buffer solution. Now, if you're wondering, how do you know it's benzoate, Mr. Dion? How do you know to leave the sodium out? Because sodium is a spectator ion, right? Sodium benzoate, CH3COOH, sodium benzoate is an ionic compound, right? It's going to dissociate completely to give me the benzoate ion, which is a weak base, okay? But it's strong enough to affect the pH of the solution, plus the sodium ion, which is not going to affect anything. And so that's why I'm interested in the conjugate base. So there we go. I have the concentration of my weak acid and the conjugate base. If I have the concentration of each of these and I have the Ka, that means I can use the Henderson-Hasselbalch equation to solve this problem, right? And that is on your handout. pH is equal to pKa plus the log of the concentration of the conjugate base divided by the concentration, of my weak acid, like that. So that means that the pH is going to be equal to the negative log of 6.5 times 10 to the negative 5 plus the log of 0.15 divided by 0.25. Okay, when we do that, we get that our pH is going to be equal to 4.19 plus negative 0.22, and we add those two together, and we end up with a pH of 3.97 for our buffer solution. And so the answer is 3.97 for number 20. All right, let's move on to 21. It says, assuming that you've got equal concentrations, so we're talking about equal concentrations of a conjugate base and acid, which one of the following mixtures is suitable for making a buffer solution with an optimum pH of 4.6 to 4.8? So we want to have a pH that's 4.6 to 4.8, but they're telling us that you have equal concentrations of the conjugate base and acid. So if we look at the Henderson-Hasselbalch equation, which is pH is equal to pKa plus the log of the concentration of the conjugate base over the concentration of the weak acid. If these two concentrations are equal, that's going to equal 1, and the log of 1 is 0, and so that means that pH is going to be equal to pKa in this situation. Okay? Now, if I want to have the pH of my buffer is being equal to 4.6 to 4.8, that means that it is acidic, right? Because the pH is below 7. So that means that my acid, and you see that I have a bunch of Kas here, my acid is going to have a Ka greater than 1.0 times 10 to the negative 7 in order to have an acidic solution. So let's look at the Kas. If we look at A, we have a Ka for our acid that is greater than 1 times 10 to the negative 7. So it's a possibility. But if we look at B, you see that the Ka for the ammonium ion is less than that, right? 10 to the negative 10. And so this will not work. If we look at the next one, which is the hypochlorite ion and hypochlorous acid has a Ka of with 10 to the negative 8. So that's too low. The next one is the nitrite ion and nitrous acid. Nitrous acid has a Ka that's greater than 1 times 10 to the negative 7. And so that's a possibility. And then if we look at the next one, it's the chloride ion and HCl. Well, HCl is a strong acid. That's going to have no Ka associated with it, and it's going to have a pH that's going to be super low, like 1, okay? So that's not going to be a possibility. So then all I would do in this case is evaluate the pH of the buffer solution in A and D. That's all I would do. So for A, we have pH is equal to the pKa. You can say, maybe I'll write it like this, pKa. It's going to be equal to the pH of the solution, which is going to be equal to the negative log of 1.8 times 10 to the negative 5. And we get that the pH is going to be equal to 4.74. And if we do the same thing for B, we say that the pH is going to be equal to the negative log of 4.5 times 10 to the negative 4. So we get that the pH is going to be equal to 3.35. And you see that this one is the correct one. And so the answer is A. It's the one that falls in that buffer range. Now, if you wanted to just evaluate the pH of everything, you could do that. But I think it's much more convenient to just eliminate these ones here that are not going to produce acidic solutions anyway. So I'd say it's a little bit faster. All right. In question 22, it says, the pH at the equivalence point of a titration may differ from 7. It's not going to be completely neutral due to what? So we have the initial concentration of the standard solution. Well, that's got nothing to do with the titration, just the initial concentration of the standard. The indicator is not going to affect what the equivalence point is, so it's not going to affect pH. The self-ionization of water is also not going to come into play. It's not going to be great enough to affect the pH. The initial pH of the unknown, again, we're talking about a titration, which is going to involve a reaction. And so the initial pH of something isn't going to count, or it's not going to affect anything after the titration is complete. But the hydrolysis of the salt formed will affect the pH. Okay? And if you're like, I'm not sure what you mean by that, Mr. Dion, what if you had, for example, the titration of a weak acid with a strong base? Why is the pH not 7 when I titrate a weak acid with a strong base? Or conversely, if you did the titration of a weak base with a strong acid, again, at equilibrium, or sorry, at the equivalence point, the pH is not going to be 7. Let's say, for example, we had a weak acid like hydrocyanic acid, right? And we were to titrate that with a strong base like sodium hydroxide. That's going to react to give us sodium cyanide plus water. And you're thinking, okay, well, that's great. Well, hold on. Sodium cyanide is going to affect the pH of the solution. Sodium won't have any effect, but cyanide will, because cyanide is the conjugate base of a weak acid. And we know that the cyanide ion that's produced, okay, right? Think about it. At equivalence point, you're going to have enough sodium hydroxide to neutralize all this, but you've produced sodium cyanide. And then cyanide is going to react with the water, and it's going to be in equilibrium because it's a weak base, and it's going to form hydrocyanic acid plus hydroxide ions. And hydroxide ions are going to affect the pH, right? Okay, so that's the kind of rationale, and we went through this in detail when we looked at the titration of weak acids and weak bases with strong bases and strong acids, respectively. Okay, let's move on to question 23. Hopefully I have enough room to solve the next few. The next few take a little bit more time, so you're gonna have to make sure that I let you have enough scratch paper for the exam. You've probably noticed that general chemistry 2 was invented by somebody who was a paper salesman. Anybody notice that? Anyhow, so if we have 24 milliliters of a 0.25 molar sodium hydroxide solution, and we're titrating it with 0.1 molar solution or 0.1 molar solution of HCl, what's the pH after you've added exactly 24 milliliters of hydrochloric acid? Let's start by writing out a balanced equation. If we take sodium hydroxide, okay, and we're titrating it with HCl, what are we going to make? We're going to make sodium chloride plus water, like that. Well, let's figure out how many moles of sodium hydroxide we're starting out with and how many moles of hydrochloric acid we're starting out with. We'll start with the sodium hydroxide. So I have a solution that's 0.25 moles per liter, right? It's told to me right here. I have my volume, which is 24 milliliters. 24 milliliters, I divide that by 1,000. So 1, 2, 3, I end up with 0.02400 liters, which is the same thing as 2.400 times 10 to the negative 12 liters. Either way works. Anyhow, so I'll just put here 0.02400 liters. We multiply those together, and we end up with the initial amount of our sodium hydroxide as being 6.0 times 10 to the negative 3 moles. Again, that's initially what we're starting out with. We do the same treatment for our HCl. We have 0.10 moles per liter multiplied by 2.400 times 10 to the negative 2 liters. And we end up with 2.4 times 10 to the negative 3 moles. Could anybody tell me which one is the limiting reactant? The sodium hydroxide or the HCl? It's not a trick question. Mr. Dion doesn't like trick questions. Yeah, thanks, Mackenzie. It's the hydrochloric acid that's going to be the limiting reactant. And so when we evaluate what our change is going to be, we're going to lose 2.4 times 10 to the negative 3 moles of sodium hydroxide, and we're going to lose all of the HCl. That's going to be gonzo. Yes, we're going to form some sodium chloride, but we're not interested in that because sodium chloride doesn't affect the pH of the solution. So at equilibrium, after the neutralization has occurred, we're going to end up with no hydrochloric acid, but we're going to end up with how many moles of sodium hydroxide? We punch this in our calculator, and we get 3.6 times 10 to the negative 3 moles. If I want to find out what the equilibrium concentration of my sodium hydroxide is, what do I have to do? I have to take that number of moles, and I'm going to divide it by the total volume. So 3.6 times 10 to the negative 3 moles divided by 24 plus 24 mils. So that's 48 milliliters, right? So I have 4.800 times 10 to the negative 2 liters, and that gives me the concentration of my sodium hydroxide as being, and I have it written down here somewhere, 7.5 times 10 to the negative 2 molar. Now we know, and I'm not going to write out a balanced equation, we know that sodium hydroxide is a strong base. It's going to ionize completely to give me the same concentration of sodium ions, but more importantly, the same concentration of hydroxide. All right, so this is just another way of saying the concentration of hydroxide is 7.5 times 10 to the negative 2 molar. So if I want to figure out the pH, I'm going to start by evaluating the pOH. pOH is equal to the negative log of the concentration of hydroxide, which is going to be equal to the negative log of 7.5 times 10 to the negative 2. I get that pOH is equal to 1.12. Again, I use 2 decimal places because I have 2 significant figures in my concentration. I get that pH is going to be equal to 14, subtract 1.12, and I get that my pH is going to be equal to 12.88 at this point. And that better be one of the answers. Yes, it's D. There we go. So 23 involves the titration of a strong base in a strong acid, and we produce a neutral salt in water. Let's take a look at question 24. It asks you, what's the pH at the equivalence point when you titrate 100 mils of hydrocyanic acid, which has a concentration of 0.1 molar, with 0.1 molar sodium hydroxide? Well, you need to know what an equivalence point is, don't you? An equivalence point is simply the point where the moles of acid are going to be equal to the number of moles of base that you've added. Moles of base, like that. Okay, so let's start by writing out a nice balanced equation for this titration. We have hydrocyanic acid plus sodium hydroxide, which is going to produce sodium cyanide plus water. So there's our balanced equation. Let's figure out how many moles of hydrocyanic acid and how many moles of sodium hydroxide we're going to need. Okay, so if for our hydrocyanic acid, we have 0.10 moles per liter, right? That's the concentration. And we're using 100 milliliters, so that's 0.100 liters. We end up with the number of moles as being 0.010 moles, right? That's how much we're starting out with for hydrocyanic acid. Now it's telling us that we're at the equivalence point. So just by that definition, we know that the number of moles of our sodium hydroxide is going to be the same, 0.010 moles of sodium hydroxide, right? I have none of this at this point. Well, there's going to be a change, isn't there? Because the weak acid is going to react with the strong base. Since they're present in equal molar amounts, I'm going to lose all of my hydrocyanic acid. I'm going to lose all of my sodium hydroxide, but what am I going to do? I'm going to produce sodium cyanide, 0.010 moles of it, aren't I? Okay, so that means that at equilibrium, I'm going to have none of this, but I'll have 0.010 moles of my sodium cyanide. Now, you know, based on what I've said already today, that sodium is not going to affect the pH of the solution, but cyanide is the conjugate base of a weak acid, so it will affect the pH of the solution. Now, it might be tempting to just start ripping and be like, oh, I'll just make a nice table where I have cyanide in water. And we looked at this already. Cyanide is going to behave as a base, form hydrocyanic acid, and I'm going to form some hydroxide ions too. But the thing is, what is the initial concentration of the cyanide? Right? We know the number of moles, but what's the total volume? I know that I added 100 milliliters of hydrocyanic acid, but in order for me to add the 0.010 moles of sodium hydroxide, what was the volume that I added? Well, you can probably figure it out in your head since it's the same concentration. It's 100 milliliters as well. So that means the total volume is 200 milliliters. If you're not sure, look, in order for me to figure out what the volume of the sodium hydroxide is, it's going to be 0.01 moles, which is what I need to reach equivalence point, divided by the concentration, 0.10 moles per liter. Look, moles cancel out, and you end up with 0.10000 liters. So the concentration of my sodium cyanide, I'm going to divide by the total volume, which is 0.200 liters, right? All I'm doing is tallying up 100 milliliters. Ooh, that didn't work. 100 milliliters from here and 100 milliliters from there. Okay. 100 plus 100 gives you 200. Okay. And that's going to give me the concentration of my sodium cyanide. Sodium cyanide, and I'm kind of running out of space here, which is equal to 5.0 times 10 to the negative 2 molar. Now, again, we know that sodium cyanide is 100% ionic. So if I have this concentration of sodium cyanide, it's going to dissociate 100% to give me the same concentration of cyanide ions. Does anybody have a question up till this point? Or give me a thumbs up if you follow me this far. Because now it's just solving the ice table at the end, which we've done, Avogadro's number of times. Feels that way, doesn't it? Thanks, Matthew. Good. I'm glad you're with me this far, because if you understand ice tables, you're going to be able to rock this part, right? One other goofy thing about this problem, and I'll probably do stuff like this in your exam, is that I've given you the Ka for hydrocyanic acid when you really want the Kb for the cyanide. Anyhow, you should know how to calculate a Kb from a Ka using the Kw. Kw is equal to Ka times Kb. So I've gone ahead and calculated the Kb already. The Kb is 2.04 times 10 to the negative 5. I have an extra sig fig in there. But yeah, so our change is going to be, we're going to lose something here, we're going to gain something here, we're going to gain the same amount. At equilibrium, I'm going to ignore the x. And the reason why is I've gone over this with you many times in class, that the initial concentration of my base is greater than 100 times the Kb, so I can ignore it. Now it's just a matter of solving the ice table. I didn't give myself really enough room to do that, so I'm going to try to stick it under here. And we get that Kb is equal to x squared over 5.0 times 10 to the negative 2, which again is equal to our Kb, which is 2.04 times 10 to the negative 5. I know I'm carrying an extra sig fig. I'll round off at the end. So we get that x, which is equal to the concentration of our hydroxide, after you solve that, is equal to 1.01 times 10 to the negative 3. Yes, I'm aware that I'm still carrying an extra sig fig. We find out that the pOH is equal to 3.00. Now I'm back to my 2 sig figs, and therefore the pH is going to be equal to 14 minus 3, which is 11.00. And so that is the pH. Okay? All right, give me a thumbs up if you follow me on that one. I feel like these are the kinds of problems that we spent a lot of time on. I feel like we solved many, many ice tables using weak acids and weak bases, using Kbs and Kas. So I'm really hoping that my students are feeling pretty confident about this. Okay. So somebody says, how do we know that sodium cyanide dissociates completely? Because sodium cyanide is ionic, right? It's ionic. Sodium cyanide is made of a metal and a polyatomic ion, which is made from non-metals. Non-metals. Okay, so it's going to dissociate completely. Now, there we go. All right. Does that help, Camden? Now, if you're thinking, well, Come on, Mr. Dion, some ionic compounds like silver iodide, that's not soluble. Well, you have to be familiar with the solubility table to some degree, Camden, okay? A little bit. But I'm not going to mix up insoluble salts in questions about titrations, okay? We've never looked at anything like that ever in our career in general chemistry too. All right, think about the KSP questions. Did I ever ask you a question that involved KSP and a completely soluble salt? Of course not. It wouldn't make any sense. Okay, so you can pretty much assume that whatever salt you make in a titration is going to be soluble. Never looked at anything that goes outside of that realm. Okay? All right. My goal is to test you on the material, not to ruin your life and confuse you. Okay? That's not the point. Okay, let's see here. Did I give myself enough room? Nope. Anyhow, it says here, calculate the pH of a solution resulting from the addition of 25 mils of 0.2 molar hydrochloric acid to 50 mils of 0.1 molar aniline. Aniline is a base. We know that because we're given a Kb here. So aniline is a base. And we're adding HCl to it. Okay, so what's going on here? We have HCl. I'm just kind of thinking here to myself. If we have HCl and we're adding it to aniline, I'm just trying to think of an easy way to represent aniline to you. You could just represent it as B, like this, and you could say that B represents aniline like that because it is a base, right? So you're going to protonate that base so that you're going to end up with Hb plus, which is called an anilinium ion, but that's neither here nor there right now. But that's going to be the conjugate acid of this base. Again, we're given the Kb for it, okay? Plus, you're going to end up with a chloride ion, all right? Well, what's the initial number of moles of our HCl that we're starting out with? Let's see if we can figure that out. We're starting out with 25 mils of a 0.2 molar solution. So we have 0.20 moles per liter multiplied by 25 mils. If we convert that to liters, we get 0.250 liters. These cancel, and we end up with, initially, we have 5.0 times 10 to the negative 3 moles of HCl. Let's do the same thing for our aniline. For aniline, we have 0.10 moles per liter, and we have 50 mils, so 0.0500 liters. That cancels out, and looky, we end up with the same number of moles, 5.0 times 10 to the negative 3 moles. And this is initially. We have none of this. Chloride isn't going to affect the pH, is it? Because chloride is the conjugate base of a strong acid, hydrochloric acid. So we don't have to stress about that a whole lot. Our change is that we're going to lose all of the HCl. It will be completely consumed, 5.0 times 10 to the negative 3. We're going to consume all of the aniline, okay, because they're present in a 1-to-1 ratio. And then we're going to end up forming some of the conjugate acid, aren't we? We're going to form 5.0 times 10 to the negative 3 moles of the conjugate acid. So that means at equilibrium, we got none of this, and we have 5.0 times 10 to the negative 3 moles of the conjugate acid. I know we have the same thing here, but we don't care about the chloride because chloride doesn't affect pH. So what's the concentration of our conjugate acid? Right, we need to know the concentration of the conjugate acid. The concentration of the conjugate acid is going to be equal to the number of moles, 5.0 times 10 to the negative 3 moles, divided by the total volume, which is 25 plus 50. So that's 75 milliliters. Let's do that in your head. 75 milliliters. And we end up with a concentration that is 6.7 times 10 to the negative 2 molar. I'm going to double check my calculation here. Sometimes I can't read my own writing. So 5 times 10 to the negative 3 divided by 0.075. Yes. There we go. So there's the concentration of our conjugate acid. Now it's just a matter of setting up a nice table, right? We have our conjugate acid, which we're going to put in water. It's going to be in equilibrium with hydronium ions plus the base. We have an initial concentration of our conjugate acid of 6.7 times 10 to the negative 2 molar. We have none of these. We're going to lose some of this. We're going to gain some of these. And then at equilibrium, we have 6.7 times 10 to the negative 2. Subtract x. Here we have x, and here we have x. Well, if we go back to the question, you notice that we were given the Kb when we needed Ka. So I went ahead and calculated the Ka. Ka is equal to the Kw over Kb. So when we work that out, we end up with a Ka, which is equal to 2.6 times 10 to the negative 5. Well, you can see that the initial concentration of the conjugate acid is greater than 100 times the Ka, and that means that we can ignore this factor right here. Now it's just a matter of solving that the Ka is equal to x squared over 6.7 times 10 to the negative 2. Again, our Ka is 2.6 times 10 to the negative 5. When we solve for that, we get the x, which is equal to the concentration of our hydronium ions, is equal to 1.32. Now I'm carrying an extra sig fig here, times 10 to the negative 3 molar. We get that our pH, which is equal to the negative log of the 1.32 times 10 to the negative 3. Yes, again, I know I'm carrying an extra sig fig. I'm just doing it for the heck of it. And I can only have 2 decimal places because I only have 2 sig figs to work with. I get that my pH is going to be equal to 2.88. And that had better be one of the answers. Yeah, it's E. There we go, like that. So just some ice tables. Again, neutralization, like that. The next one is kind of a conceptual problem, isn't it? It says here, which of the following substances has the greatest solubility in water? And we're given a bunch of KSPs, right? We're given the KSP for all of these. Do you guys know what the relationship between KSP is and our ions, right? If we have a solid, like let's say, oops, I didn't want to do that. Let's say we have, let's just think about our lead 2 iodide, the first one. If we have lead 2 iodide, right, in equilibrium with lead 2 ions plus iodide ions, like that, our KSP is going to be equal to the concentration of lead 2 plus times the concentration of iodide squared. So that means that the greater the KSP, the higher the KSP, so higher KSP equals greatest, you could say greatest formation of ions, which is another way of saying greatest solubility. Okay, like that. So if I look at all of the different KSPs, could anybody tell me which one of these is going to be the most soluble? And it's not a trick. Mr. Dion hates tricks. I just put here. Yeah, exactly. Silver sulfate, right? It's got the highest KSP. Therefore, it's going to be the most soluble. Son of a gun. There we go. That's kind of just a conceptual, right? I would call that really a conceptual question. There's no math required. Just looking at the numbers and understanding what they mean. Okay, thanks everybody that answered. I really appreciate that. I love it when my students answer some questions. Next one's a KSP problem. We solved problems like this Avogadro's number of times, right? When we looked at chapter 15, it just says calculate the solubility, which is the same thing as the molar solubility. It means the exact same thing. Solubility of strontium fluoride in pure water, and they give us a KSP. All you have to do is know how to set up an ice table and use a KSP. You start with strontium fluoride, right, which is a solid. It's going to be in equilibrium with strontium ions and twice the amount of fluoride ions. We start with an initial amount of the solid. We don't have any of these. We're going to have some kind of change. We're going to produce X and 2X of the strontium ion and the fluoride ions respectively. right? Because the stoichiometric ratio is 1 to 2 for strontium ions to fluoride ions. At equilibrium, we don't have to worry about the concentration of a solid. We have X here and we have 2X here. Our KSP for this equation is going to be equal to the concentration of strontium ions times the concentration of fluoride ions squared, which is going to be equal to X times 2X squared, which is going to be equal to 4X cubed. All right. So that means that 4X cubed is going to be equal to our KSP, 2.6 times 10 to the negative 9. So that means that X is going to be equal to the cube root of 2.6 times 10 to the negative 9 divided by 4. So we get that X, which is our molar solubility, right? It's the amount of strontium fluoride that went into solution, is equal to 8.7 times 10 to the negative 4 molar. Again, if you don't know how to take a cube root on your calculator, another option would simply be, the word I was looking for was alternative. An alternative would just be to put it to the power of a third, like that, if you're really handy with your exponent button. Either way, you're going to end up with the right answer. Give me a thumbs up if you follow me on that one. I feel like we spent a lot of time on these, and I want to make sure my students can nail a problem. If you have a problem like this, I want to see some good results from my students. I would like everybody to get this correct. I'd like everybody to get everything correct, but I'd especially would be heartbroken if my students didn't do well on this question. Let's see. Question 28, another one. We tried a few of these. Just, it says, are you going to make a precipitate of magnesium fluoride? They give us the KSP of magnesium fluoride here. Will you make some magnesium fluoride precipitate if you mix 200 mils of magnesium chloride with 300 mils of sodium fluoride? Camden, you notice that, look, they're telling you that if you have this, you're mixing 200 milliliters of the magnesium chloride, right? That infers that it's soluble, right? If you have a solution, they're telling you it's a solution, right? They give you a concentration. Same thing for the sodium fluoride. Again, if you don't have the solubility table memorized, which is a good idea to know your way around it at this point in the class, but if you have a solution of sodium fluoride, they're telling you it's soluble, right? If you have a solution, why the hell, it has to be soluble, okay? And if they gave you a KSP for magnesium fluoride, it tells you that it's insoluble, right? So they kind of give you all the information that you need. So all we're going to do, you can tell just by looking at the possible answers, is we're going to calculate Q based off of the concentration of magnesium ions and the concentration of fluoride ions, right? Because we know that our Q, right, since magnesium fluoride is a solid, it's going to be in equilibrium with magnesium ions and twice the amount of fluoride ions. So our KSP is going to be equal to the concentration of magnesium ions times the concentration of fluoride ions squared. Okay, so all we need to do is to calculate Q with the concentrations of the two ions that we have, and then we're just going to evaluate Q compared to KSP. So we'll do that after. All right, so let's figure out what the concentration of magnesium is first. So we'll start with the magnesium chloride. So we'll start with from magnesium chloride. So Camden, again, it's going to be completely soluble, right? They're telling you that you're making a beautiful solution, which is going to be magnesium ions plus twice the amount of chloride ions. So if the concentration of my magnesium chloride is 1.9 times 10 to the negative 3 moles per liter, and I have 200 milliliters, that's 0.200 liters. That means that I have 3.8 times 10 to the negative 4 moles of magnesium chloride. Since the ratio is 1 to 1 for my mag chloride to my magnesium, that means that I also have 3.8 times 10 to the negative 4 moles of magnesium 2 plus. Give me a thumbs up if you follow me thus far, and if you don't, stop me and tell me what you don't understand. Did my students follow me? And again, if you don't be afraid to raise your hand and just say, okay, all right. Again, if you don't understand, stop me. But I feel like good. Thanks, Brogan. Good, good. Okay, so we know the number of moles of magnesium. Beautiful. That's just wonderful. Now let's figure out the number of moles of fluoride. So from our sodium fluoride, right? So now we're going to work with the sodium fluoride. We know that sodium fluoride is going to break apart to give us sodium ions plus fluoride ions. So if I have, what's the concentration? 1.4 times 10 to the negative 2 moles per liter for my sodium fluoride. And I'm using 300 milliliters, so I multiply by 0.300 liters. I end up with the number of moles of sodium fluoride as being 4.2 times 10 to the negative 3 moles. That means, again, since the ratio is 1 sodium fluoride to 1 fluoride, that means that I have the exact same number of moles of fluoride. 4.2 times 10 to the negative, what is it, negative 3 moles of fluoride. Okay, again, wonderful. That's all well and good, but we need the concentration of them. So in order to evaluate the concentration of magnesium ions and fluoride, we're going to have to divide both of them by the total volume. What's my total volume? I have 300 milliliters plus 200 milliliters. That gives me 500 milliliters, which is half a liter. So divide by 0.500 liters, by 0.500 liters. And now we're really getting somewhere. We get that. The concentration, and I'm kind of running out of space here, so the concentration of our magnesium 2 plus, and I've already calculated this, and it's somewhere here. It's 7.6 times 10 to the negative 4 molar. I get that the concentration of my fluoride is equal to 8.4 times 10 to the negative 3 molar. Hot dog, we have a wiener. I got the concentration of my magnesium. I got the concentration of my fluoride. I got my expression for my Q. Let's do it up. So we're going to get that our Q is equal to, and you can call it QSP if you want, I don't care. It's going to be equal to 7.6 times 10 to the negative 4 from our magnesium multiplied by 8.4 times 10 to the negative 3 squared from our fluoride. We get that Q is equal to 5.4 times 10 to the negative 8. What was our KSP? 6.9 times 10 to the 9. Our Q is greater than our KSP. So you can see that some of them have, only one of them, pardon me, only one of them has Q greater than KSP. I wanted to ask you guys if a precipitate would form. Well, hopefully you understand that if you exceed the KSP with the concentrations, that a precipitate will form. So we'll put here, therefore precipitate will form. All right, here we go. So the answer is A. All right, I should have put another one. Yes, or Q is greater than KSP, and then I should have put a no next to it. Anyhow, whatever. It's too late to go back now. Everybody with me on that one? You can pretty much expect that I'm going to ask a question similar to this on the actual exam, where you have to evaluate a Q, right? We talked about Q a little bit. Class? Good, thanks. Good, good, good. All right. What's question 29 about? All right. Great thing about general chemistry, too, is, you kind of feel like every question you answer is like a little victory, Okay. Question 29 says the concentration of the complex ion in each of the following solutions is 1.00 molar. In which of the solutions will the concentration of the uncomplexed metal ion be the smallest? This one I read it twice because I kind of did the exam by myself really, really quickly. And it says uncomplexed metal ion. So that means that the metal ion is in solution, right? If it's not complex, because these are all complexes here. Remember the complex ion that I told you that I always call them coordination complexes? Coordination complex. It's the same thing as a complex ion, okay? Exact same thing. So let's say we were just dealing with the first one, right? What the hell is KF? KF is a K formation, right? the higher the Kf, the more stable the compound. Remember that? Sometimes we call it a stability constant, I said. So if the Kf is high, it means greater stability, which means that more of the complex would be formed, the coordination complex. If the Kf is low, it means lower stability. And again, just taking the example of the first one, what is Kf, right? Kf would be Hg2 plus 4 cyanide ions, right? Gives you the coordination complex. Yeah, 2 minus, like that. So that's the formation. So again, whichever one has the highest formation, or Kf, K formation, is going to have less ions in solution, right? Because it's going to have the equilibrium pushed more to this side, okay, to the coordination complex. So based off of all my dog and pony show that I just gave you, could anybody tell me which one of these is going to have the uncomplexed metal ion, so in this case it would be the mercury, in the lowest concentration? And it's not a trick. It's just understanding what Kf means. Yeah, thanks. Good, Katie. Great. Glad you corrected yourself, right? So again, since A has the highest Kf, that means the equilibrium is going to be farthest to the complex since it's a formation, right? So that means you're only going to have a little bit, tiny bit of that left over. So the answer is whichever one has the greatest stability, right? It's going to, you could put it a whole bunch of other ways. You could say more complex formed, therefore less ions in solution. Okay, that's just another way of looking at it. Okay, let's move on to question 30. It says, calculate the molar solubility of iron 2 hydroxide in a solution with a pH of 13.5. Look, if we write out an equilibrium expression for iron 2 hydroxide, right, Camden, if iron 2 hydroxide is showing up in a problem about molar solubility and you got KSPs, that tells you it's an insoluble compound, right? We can say it's insoluble, but it's going to be in equilibrium with some iron 2 plus ions plus twice the amount of hydroxide ions. Well, initially, we don't consider the concentration of a solid. We have none of this, but it's telling us that the pH is 13.5, which is basic, which suggests that we have some hydroxide in there, don't we? So we need to figure out what our initial concentration of hydroxide is. Let's do it. If the pH is equal to 13.15, that means that the pOH is going to be equal to 14. Subtract 13.15, which is going to equal 0.85. And then the concentration of the hydroxide is going to be 10 to the negative pOH, which is equal to 10 to the negative 0.85. So we get that the concentration of the hydroxide initially, since our solution has this pH, is going to be 1.4 times 10 to the negative 1 molar. So 0.14 molar. Well, I have my 1.4 times 10 to the negative 1 molar here. I'm going to have some kind of change. I'm going to gain something here. I'm going to gain twice as much here. And then at equilibrium, again, I don't consider the concentration of a solid. I'm going to have x here. And then I'd have 1.4 times 10 to the negative 1 plus 2x. Well, I'm given the KSP, and you can see that this initial concentration is way bigger than 100 times my KSP. And so I'm going to ignore the plus 2x like that. So I get that my KSP, which is equal to the concentration of iron 2 plus ions times the concentration of hydroxide ions squared. I get that the concentration of my iron 2 plus, which is my molar solubility, is going to be equal to KSP divided by the concentration of the hydroxide squared. That equals 1.6 times 10 to the negative 14. Remember, that was given to me right here. divided by 1.4 times 10 to the negative 1, all of that squared. And when I punch that in my calculator, I get that it's equal to 1.6 times 10 to the negative 14 divided by 0.01995. I know I'm carrying extra sig figs. I'll round off at the end. And I get that the concentration of my iron 2 plus ions, which is the molar solubility, is equal to 8.0 times 10 to the negative negative 13. Yeah, 13 molar. Okay, so that is this answer right here. I just made a note for myself when I solved this one. I was trying to evaluate this. So you could add the 2x, Brogan. You can totally add. Could we have set that to 2x? No, no, because it's not 2x. Okay, you're adding 2x to it. Okay, so no, we can't do that. And just to prove it, if you take 1.4 times 10 to the negative 1 and you divide it by 2, you get 7 times 10 to the negative 2, which is several million times higher concentration than this. So that won't work. Okay, where are we? There we go. So you'd be way off in left field with that one. I'm just kind of thinking to myself here, but I made some notes to myself. So sometimes I carry extra sig figs. So if you try this problem at home by yourself, if you carry an extra sig fig here for the concentration of your hydroxide ion, you'll get that it's 1.41 times 10 to the negative 1. If you do that, if you plug 1.41 in here, you actually end up with not 8.0 times 10 to the negative 13. In that case, you end up with 8.2 times 10 to the negative 13 molar. But again, I don't give you any answer where I'm splitting hairs like that. So it would be abundantly clear that you would have the right answer. Okay. Again, my purpose is not to try to trip you up. It's just to make sure that you're able to solve the problem. Okay. So even if you rounded it a little bit different, you're still going to get the right answer. Well, with all that in mind, since I forgot to put questions 13 and 14 into the video, and I know I recorded them, I must have just edited them out by accident. Let's take a look at them. You can even see my chicken scratch here, and I'm not going to delete it. This one just says arrange these acids, H2SE, H2TE, H2S. So you see that selenium, tellurium, and sulfur are all in group 16, and we talked about the relative strengths of acids based on atoms that are in the same group. And we said that as the central atom increases in size, the bonds get bigger. They get longer and they get weaker because the size of the atom is bigger, right? As you move down a period. And so if the bond is weaker, the molecule is going to be more prone to lose a proton, and therefore it's going to be more acidic. So it would just be going from tellurium to the selenium to the sulfur. So the one with the tellurium will be the most acidic, and the H2S will be least acidic. The next one, number 14, maybe I could erase this so we could kind of start over. On number 14, it just says, which one of these represents the net ionic equation of the reaction of a strong acid with a weak base? Well, if you look at A, this one represents a strong acid plus a strong base. We've looked at several examples of that. If you look at C, hydroxide is a strong base, but hydrocyanic acid is a weak acid. And we're looking for strong acid with weak base, so that's not a possibility. If you look at D, hydrocyanic acid is a weak acid, and CH3NH2, that's actually a weak base. How do I know it's a weak base? First of all, it's not a strong base. It's not in our list of strong bases, which you should know. The group 1A and 2A hydroxides that we've looked at that are strong bases. Also, you can see that it's accepting a proton. So therefore, it must be a base. So ergo, it must be a weak base. So that is also not the answer. But if we look at B, H plus is a strong acid, and this CH3 NH2, this is called methylamine. must be a weak base. Why? Because it's not a strong base and it is accepting a proton. Right? If it's a proton acceptor, it's a Bronsted base. And so the answer is A.